Hi, I'm Vidhi, and my presentation is about evaluating plasma pathways for bright train CO2 utilization. Next slide, please. Freight rail is a major emission source, but it's very difficult to decarbonize. US freight rail emits around 35 million tons of CO2 per year, moves about 40% of long distance freight, and less than 1% of the rail network is electrified. This makes most locomotives still run on diesel. And that makes rail a meaningful source of emissions at a national scale, but also a very difficult one to address because those emissions are spread across rail networks instead of coming from one stationary source. At scale, the obvious alternatives are also very difficult. Electrifying freight rail with overhead wires would require major infrastructure build-out and trillions in investment, while battery electric freight is limited by weight, with estimates suggesting up to a third of train cars would need to be dedicated to batteries. Because of that, major US rail operators are instead looking at lower carbon liquid fuels like renewable biodiesel as a more practical near-term pathway. Next slide, please. CO2 by itself is very stable, which makes it difficult to use directly and limits its values on its own. But if it's converted into intermediates like carbon monoxide or syngas, it becomes much more useful as a chemical feedstock. Those intermediates can then be used to produce fuels, chemicals, and other industrial products that have already established demand. So the goal here isn't just carbon capture, it's turning CO2 from a waste product into something that can be used more productively. Next slide, please. The main reason plasma is interesting for activating CO2 is that it activates CO2 differently than traditional thermochemical systems. Conventional thermochemical processes rely on bulk heat, which means high temperature and large centralized systems. And plasma differs in this by instead using high energy electrons to drive the reaction. So you can actually activate CO2 without actually having to heat up the entire gas stream. Next slide, please. So my research question was informed by this, which was which plasma pathway is the most practical for this type of conversion? And to answer this question, I reviewed 35 papers and compared three major plasma pathways, which were dielectric barrier discharge plasma, or better known as DBD plasma, microwave plasma, and lastly, gliding arc plasma. And I evaluated them on the basis of their efficiency, the products that they make, and also their scalability. So how hard it is for it to go from a lab pilot-based setting to actually being used commercially in industrial settings. And what I found about DBD plasma is that it produces mainly carbon monoxide, and it works very well with catalysts, which offers really good control and selectivity. But some limitations of DBD plasma is that it has low energy efficiency and limited throughput, which makes it very difficult for it to actually be scaled from just a lab setting to industrial settings. With microwave plasma, what I found is that it directly splits CO2 into carbon monoxide, and that direct splitting allows for it to achieve really high conversion, but it requires at the same time high energy input and oxygen separation, which lowers the overall efficiency of the system. And it also makes scaling more complex because it makes it a lot more expensive to go into industrial settings. And lastly, with gliding arc plasma, I found that it kind of differs from the other two because it produces syngas, which is carbon monoxide and H2 in one single step. And right now, syngas is already widely used to make lots of fuels, chemicals, and materials. So it already offers that good product control. And it also has moderate efficiency, but it supports really high flow rates and continuous operation. So out of the three, it's the most easiest to be scaled in industrial settings. So overall, although all three pathways are feasible, their main limitations really come down to their energy efficiency and the reactor design. And although as of right now, plasma isn't fully commercial yet, it seems that gliding arc is the most practical direction because it produces a useful product and it's the most compatible with scaling up from just a lab setting to industrial settings.